Now for the most confusing part of statics, we have vectors in 3 dimensions, or 3D vectors. So, what makes 3D vectors so complicated? It's basically because to define a 3D vector, you need your magnitude, but you also need at least 3 angles. Now, these angles are maybe the most confusing part of all of this. They are theta x, theta y, and theta z. These are angles formed by creating 3 right triangles with the x, y, and z axes and the force. And forgive me, these are not angles, these are triangles. They are angles formed by creating 3 right triangles with the x, y, and z axes as the base. Now, when we form these triangles, the triangles do not align with the other 2 axes. So what they do is, for example, theta x is the angle between this force vector F acting through space. It's going to create a triangle, but the triangle does not lie on the YZ or the ZX plane. It's acting on a random plane whose base goes through the x-axis, but it is acting at an angle in space to the other 2 axes. And a plane, mathematically, is a flat surface which is infinitely large and requires 2 dimensions. Each of these things can be a projection can be made from the tip of the force down to each of the axes. And to get the final one on the z-axis, you have to project straight down. And I'll use the red here to project down. And lying here, I have a distance here, distance here, distance here. This distance in the foreground is AZ. Correction, that is AX. This distance here on the side is AZ. And this distance up, or the projection, is AY. AX, AY, and AZ are the rectangular components of the force vector. Now, just to make things absolutely clear, this is the same force vector, right? We're going to look at it in terms of theta x, theta y, and theta z. Now, starting with theta x, if we look at what our definitions of the thetas were, we're going to say that for theta x, the base of the plane created is the x-axis. So this is the x-axis. The y-axis is some random axis. We don't know what this is. It's a random plane we don't understand. So I'm going to label it random. If we have theta x and we find the x component of this, this gives us our a sub x. And we can say that the cosine of theta x is equal to ax over the total magnitude of the force. If we look at theta y, this axis here is the y-axis. The axis on the bottom is some random axis. And the cosine of theta y is equal to ay over f. Finally, if we come down here to theta z, we find that this is the z-axis, this is a random axis, the projection down here gives us a sub z, and the cosine of theta z is equal to az over f. If we want to know what f is based on the rectangular coordinates ax, ay, and az, we can use Pythagorean theorem again and say that the force is equal to the square root of ax squared plus ay squared plus az squared. But remember that theta x, theta y, and theta z is an angle between the force and the x, y, and z axis. The other axis is some random axis acting through the other two dimensions. It does not align with y or z. It is random. Now, there is another way, or an older way, of representing a three-dimensional vector. You can also represent a three-dimensional vector with the magnitude and two other angles. These two angles are given as phi, where phi is called the azimuth angle, and theta, where theta is called the transverse angle. So the azimuth angle is directly taken between the force vector and the y-axis. The azimuth angle is taken as if you project the tip of the force down onto the zx plane and you draw another line out to meet it that meets it perpendicularly. The transverse angle is measured from the z or the x-axis to this projection. Now, from this, we can work out the rectangular components. And this would be, if you're given a force with an azimuth and a transverse angle, I would 100% turn it into AX, AY, and AZ. From there, you could get theta X, theta Y, and theta Z, and you can go about doing whatever you need to do with your force vectors. So let's say that our force is now 20 kips. And if you've never dealt with a kip is a kilopound. So 1 kip equals 1,000 pounds. We're going to have an azimuth angle of 25 degrees. And we're going to have a transverse angle measured from the z-axis of 30 degrees. Now, I can use these angles to get myself back to AX, AY, and AZ in the following way. Now, AY is pretty simple. AY is just going to be equal to the force magnitude of 20 times the cosine of 25. And that will equal 18.1 pounds. Oh, 18.1 kips. That one's straight away because the azimuth angle phi gives us the angle between the force and the y-axis. It is basically theta y. In order to find out our AX and AZ components, we need to figure out what the length of this projection is. Generally, I call that projection A prime. A prime is just going to be equal to the force magnitude of 20 times the cosine of 90 minus the azimuth angle. So we're finding this angle down here between the force vector and the projection. In this case, it's going to be 8.45 kips. Once we have that 8.45, we can then calculate our AZ and our AX. AZ is going to be equal to 8.45 cosine of 30, which equals 7.32 kips, and AY is going to be 8.45 cosine of 90 minus 30, which is going to equal 4.22 kips. Okay? Now, when we're doing work, understanding if we did it right is really important. So what we did is we took a 20 kip force and broke it into its AY, AZ, and AX components. If we put it back together, it should equal these 20 kips. So if I say the force is equal to the square root of AX squared plus AY squared plus AZ squared, it needs to be equal to, in the end, 20 kips. So if I do this, I find that I have 18.1 squared plus 7.32 squared plus 4.22 squared. And if I do all that out, I find that this comes out, the force is equal to about 19.999, which is close to 20. So we did a good job finding our AY, AZ, and AX. But realistically, the first thing you want to do if you're presented with a force with an azimuth and a transverse angle is get it into rectangular coordinates, because they're much easier to work with. Now, you have probably seen AY, AZ, and AX in your physics class. What that is your I, J, and again K notation. So it would have been much nicer, instead of saying that this is 20 kips with a azimuth angle of 25 and a transverse angle of 30, to tell you you have a force that is equal to 4.22 I plus 18.1 J plus 7.32 K. This is a much easier way of representing a force, because everything is contained in this and you can operate on it directly. So let's say that we have another 10 kip force, and now our force is equal to 8 kips. And I want to color coordinate, so we'll make this green. And our 8 kip force has a theta x equal to 54.7 degrees, a theta y equal to 54.7 degrees, and a theta z equal to 54.7 degrees. Our 10 kip force has a theta x equal to 80, a theta y equal to 10, and a theta z equal to 90. If we have our vectors defined in this way, the easiest way to add these things together is to turn them into I, J, and K notation. Then we can directly add I, J, and K together. So when we're adding, again, we need to take care of the magnitude and the direction. So we can say that A, or let's call not so A, but our 8 kip force, we can call A. Our 10 kip force, we can call B. And then we can say that A is equal to 8 times the cosine of 54.7 plus the cosine of 54.7 plus the cosine of 54.7. These cosine and sines are based on our definitions for our theta x. We said that, for example, theta x is equal to, or the cosine of theta x is equal to ax over the force. That is, these three cosines are just based on theta x, theta y, and theta z. So we can define our vector in this way. We can define vector b and say it's equal to 10 times cosine of 80 plus cosine of 10 plus cosine of 90. And all these are I, j, and k, and I, j, and k. So what we can do is add them together directly. We can say that A equals 4.622I plus 4.622J plus 4.622K. B equals 1.737I plus 9.898J plus 0K. If we add them together, we get a total of 6.359I plus 14.471J plus 4.622K. So if you have vectors and you break them down into your I, J, and K notation, you can do addition directly by adding the X, Y, and Z components, or the I, J, and K components. Now, one thing when we wrote this down here, we kept the magnitudes of 10 and 8 outside of these brackets. So what we have stored in the brackets represents only direction. And since it's direction without magnitude, we are left with something called the unit vector. And a unit vector has a magnitude of 1, so it gives purely direction.